What's up, everybody? It's Dan from SageMathTutoring.com, and here we have a video pertaining to the power series, specifically radius of convergence and interval of convergence. This is a topic that can come up on the AP Calc test BC. So before we dive into the process of figuring out the radius of convergence and the interval of convergence, I'd like to just talk about some broad concepts in general, including the power series in general. So the power series is a series that would take these forms. It's either going to be a sub n times x raised to the n power, which would look like this if you were to sort of work all of that out. And it could also be the case that we have an x minus c raised to the n power, which of course would look like this if we were to begin the process of adding everything. So c is going to be the center, okay, the center. Now, to kind of zoom out a little bit more, it's important to recognize that there are going to be certain values for x that would result in this power series converging, okay? Depending on what a sub n is or what have you, right? And there are going to be certain values of x where this power series would not converge, okay? So what we're doing with these problems on the AP Calc exam is we're figuring out which values of x would be such that it would cause this power series to indeed converge, okay? Now, the domain of a power series is the set of all x values for which the power series converges, okay? So I'll say that again. The domain of a power series is the set of all x values for which the power series converges, okay? So I think as we proceed, that's going to be a little bit more clear. It is the case that the center will always be part of the domain. So let's look at three ways a power series might converge. So the first way is that the power series might converge to an interval. In other words, there's going to be a sort of range of x values such that if you were to substitute x back in, then it would result in a power series that converges, okay? So that's the case, and this red line represents that particular interval of x values between a and b that would result in this power series being a series that converges. And the x equals c is the center. Once again, c is the center. Now, by the way, this says x minus 0 raised to the n power, so the center in this case would be 0. So c is the center, and what we refer to as the radius is the distance between the center and one of these sort of endpoints of the interval, okay? So that's the first way a power series might converge. The second way is that it might converge to literally all real numbers. So in other words, x could be anything, any real number, and if we were to substitute it back in, it could be the case that the power series would nonetheless converge, regardless of which number you put in for x. And the third way that a power series could converge is to the center at x equals c. So in other words, the center, c, is the only value of x that would cause the power series to converge. Okay, so hopefully that makes sense. So how do you find out what the interval of convergence is? Well, first of all, let's be very clear. If you had the interval of convergence, finding the radius of convergence would not be too difficult, right? Because if you had this interval, we know that the radius is just half the total length of the interval itself. Okay, so it should be easy to find. So how do you find the interval of convergence? Well, you would have to use the ratio test, which is something that many students in AP Calculus are kind of familiar with at this point. By the time you get to interval convergence subtopic, you should be pretty familiar with the ratio test, but the way that you're going to use the ratio test is very specific when it comes to these problems. So what you will do is you would find the limit as n approaches infinity of a sub n plus 1 all over a sub n, so that should seem pretty familiar. And if it's the case that the this ends up being something less than 1, then the series converges to an interval. If the limit as n approaches infinity of this absolute value equals 0, then the series converges for all values of x. And if the limit as n approaches infinity equals infinity, then the series converges only to the center. So these are the things that you need to remember. Now, one thing that's definitely very helpful is if it's the case that you discover that you perform this test and it does not equal 0 and it does not produce infinity, then the option you will be defaulting to is this first option. Okay, so all you need to know, in other words, that we're dealing with the first option is if it turns out that this does not produce a 0 and it does not produce infinity. Okay, so let's get to some problems. So looking at this one, find the radius of convergence of the series. So I'm going to say we should find the interval of convergence first, or at least get a sense of what the interval might be, okay? My student got this wrong for a pretty specific reason that we're going to cover soon, but we're not going to find the exact interval yet. We want to get a sense of the interval first. So all you have to do is perform that, ratio test for this, and let's see what happens. Probably a good idea to get clear on what your a sub n plus 1 is. That's going to be x to the n plus 1 all over 4 times n plus 1 minus 1. And of course, our a sub n is just x to the n power all over 4n minus 1. So all you have to do from here is perform that test. So we're going to do the limit as n approaches infinity of the absolute value. So it's going to be this divided by that. So let me just write the a sub n plus 1 first. And we have this. And it's going to be times the reciprocal of a sub n, which is 4n minus 1 all over x to the n power. So we need to find out, well, what does this equal? Well, it is the case that the x to the n plus 1 could be rewritten as x to the n times another x. So in fact, I prefer that, so I'm going to just cross that out. It's also the case that we could indeed distribute the 4 down here, so we would have 4n. I guess that would be plus 4 minus 1, so that would be plus 3. So we can kind of get rid of that too. Now it's the case that the x to the n's would cancel. And therefore, we are really just trying to figure out the limit as n approaches infinity. Looks like it's going to be x times this sort of fraction here, which is 4n minus 1 all over 4n plus 3. Now, if you were to substitute infinity in for n, this would end up being 4 over 4, also known as 1. So this would sort of just cancel out. You could think of it that way. So at the end of the day, this equals the absolute value of x. Now, seeing as how that did not produce a 0, and seeing as how that did not produce an infinity, we can therefore say that we're dealing with this scenario, and therefore we are going to actually set that equal, or we could say set that less than 1. All right, so that's what we're dealing with. It turns out that this is less than 1. So we could kind of write it like that. That's what it turns out to be. So another way of writing that situation is that x is going to be between 1 and negative 1. Now that actually gives us a sense of the interval. Okay, that gives us a sense of the interval. So I'm going to draw it. We have a negative 1, we have a 1, and we have everything in between. So the center appears to be 0, and therefore the radius is going to be 1, okay? And that's why this answer ended up being correct. But we need to find the interval of convergence to the series. Now the problem is we need to test these end cap values. And if you test out 1 and that results in divergence, then 1 is not included in this interval. If you test out 1 and it results in convergence, then 1 is included in the interval. And the same goes for -1. If you test out -1 and -1 results in divergence, then it's not going to be included in the interval. And if you test out -1 and it results in convergence, then it will be included in the interval. So we have to kind of see what happens when we test out x equals 1 and x equals -1, okay? So let's test out what happens when x equals 1. So if we were to kind of consider this, it would be just 1 to the n power, which is really just 1, all over 4n minus 1. So the question is does that converge or diverge? So this is where the direct comparison test could come in to help us. So what we could do is we could figure out another sort of expression. In this case, we're going to find an expression that is slightly, we could say, smaller than this one. And if it turns out that the smaller expression that's somewhat similar to this diverges, then that means this has to diverge, okay? So that's mentioned here, okay? So we're going to find a b sub n that happens to be smaller than our current a sub n right now, and a good candidate for that would be something like this, something like 1 over 4n. Now that actually is smaller than this, and the reason is because we could say this denominator is larger. Okay, the denominator is larger because this is 4n, but this is 4n minus 1. So clearly the denominator here is larger, which means that the fraction itself is smaller, seeing as how the numerators are the same. Now, this is known to diverge, and we know that because that is what we call a harmonic series. Okay, so you might be wondering how that would be. Well, the reality is that we could rewrite this whole thing with the sort of 1/4 out front, okay? And then you would have this, and then you would have just 1 over n there. And the sort of exponent that's hovering above that n is a 1, and therefore, due to this sort of p-series test concept, we know that if p equals 1, in other words, if that exponent is 1, it's the harmonic series, and the harmonic series always diverges, okay? So that diverges. So through the comparison test, we were able to find a comparable expression, one that represented a fraction that was sort of slightly less than this, okay, but it was still comparable. We recognize that this new expression diverges, which means that this also has to diverge. In other words, if this thing shoots off into infinity, seeing as how this expression is above that, that's also going to have to shoot up off into infinity. You kind of think of it that way. So we know for a fact that there needs to be a parentheses next to +1. So my student did that correctly. But it is the case that +1 is not included in the interval. So now, of course, the question is, well, what about when we plug in -1 into that? Well, if we were to plug in -1 into this series here, in for x, it would become -1 raised to the n, we could say times 1 over 4n minus 1. Now, it's the case that with this is an alternating series, which would bring us to the alternating series test, which is right here, where basically what you'll do is you're going to compare variations of this part right here. And you just take a look and see, is a sub n plus 1 less than a sub n? And if that's the case, then the series converges. So let's actually take a look at that. is the following true? Is the following true that 1 over 4 times n plus 1 minus 1, is it true that this is less than 1 over 4n minus 1? Well, let's take a look. Let's see. So if we were to distribute that down there, it would be 4n plus 3. Let's kind of get rid of that. So this denominator is larger than that denominator, which means that the entire fraction itself is smaller. So it turns out that when you plug in -1 for x, this converges. Okay, it converges. So seeing as how when you plug in -1 for x, it converges, that means that this should get a bracket right here. That should get a bracket. Okay, so looking at the next. Okay, so for this one, obviously, we're going to be doing the same thing. So let's find a sub n plus 1 first. And that would be x raised to the n plus 1 plus 2 up there, all over 3 times n plus 1 factorial. And we have a sub n is the original, which is x to the n plus 2, all over 3n factorial. So at this point, we can then perform the ratio test, and that would be a matter of doing the limit as n approaches infinity of really the first thing, the a sub n plus 1 variation, all over 3 times n plus 1 factorial, and it's going to be that times the reciprocal of this. So it is the case that up here we're really looking at x to the n plus 3. So we can kind of cross that out. And down here we're looking at 3 times n plus 1 times n factorial. So we can cross that out. And the 3's would cancel. The n factorials would cancel. And if we were to analyze this one further, it would really be x times x to the n plus 2, if you think about it, right? So we can kind of cross that out. And therefore, hopefully we can see that the x to the n plus 2 will cancel. So therefore, what we're dealing with is the limit as n approaches infinity of x over n plus 1. And when we put in infinity there, well, that's just going to become 0, because this denominator would get infinitely large. And you could also sort of recognize that this could be rewritten as the limit as n approaches infinity of x times 1 over n plus 1. And seeing as how this part would become 0, well, it would be 0 times x, and that equals 0. So according to our structure, if we perform the ratio test and it equals 0, the series converges for all values of x. So therefore, the so-called radius would be infinity, and the interval should be all real numbers. All right, so that's that one. Okay, looking at problem number 5, find the radius of convergence. I say we just kind of cut to the chase with the ratio test. I think we're all getting the hang of it by now. So we're looking at 5 to the n plus 1 times n plus 1 to the 2 times x to the n plus 1. And we would be dividing that, really, by the original, x to the n right there. Now, it is the case that 5 to the n plus 1 is really just 5 to the n times yet another 5, so we can cross that out. It is the case that x to the n plus 1 is really x times x to the n, so we can cross that out. And therefore we can see some cancellations, 5 to the n's. The x to the n's would cancel. And the next thing we know, we have the limit as n approaches infinity for 5 times n plus 1 squared times x all over n squared. Okay, and I think that's it, right? So I'm going to rewrite that in a way that helps us sort of understand the situation a little bit better. That's really 5x times n plus 1 squared all over n squared. Now, when we substitute infinity in for n, notice how the power of this n is the same as the power of this n. So the degrees are the same, because if we were to FOIL that, we would have an n squared as the leading term. So whenever the power is the same in that regard, this would just be 1. So at the end of the day, this is going to be 5x times 1, which is just absolute value of 5x. Now, as I said before, since this is not equal to 0, and since it's not equal to infinity, we need to treat it like this one. So we're going to go ahead and say, okay, absolute value of 5x is less than 1. So therefore, we can say that 5x is between 1 and negative 1. So x is therefore less than 1/5 and greater than negative 1/5. So if we were to sort of think of an interval, we would have negative 1/5, we would have positive 1/5, and we would have everything in between. That looks like that would be a 0 in there. And the radius would therefore be 1/5. So that should be 1/5 right there. Now, of course, the interval is such that we would have to test 1/5, and we would have to test negative 1/5. So let's take a look. If we were to substitute positive 1/5 in for x, we would have the following series. We would have this. Okay. Now, this is a good candidate for the nth term test for divergence, which basically says if the limit of this whole expression as n approaches infinity does not equal 0, then the series diverges, okay? Now, for the record, it kind of looks like a geometric series, but the problem is these are constantly changing, so it's not a geometric series, and therefore we're better off with this test. So if we were to rewrite that in a way that would be a little better, it would be to recognize that we're really dealing with 5 to the n times n squared all over another 5 to the n, because this blue 5 to the n is right here, and that's being raised to the n power. So it's the case, therefore, that these would cancel, and when we plug in infinity into this, that clearly does not equal 0, so that's all we need to know. And if we were to substitute negative 1/5 in there, that would be the final step in the process. So substituting negative 1/5, well, in a way that would sort of result in a slightly similar situation, only this time you would have a negative 1 being raised to the n, and that would be times 5 to the n times n squared all over another 5 to the n. So I kind of did a couple moves at once. Number one, I extracted a negative 1 here, and it became negative 1 to the n. That left us with just a 1/5 to the n power, which we already know from the last example could simply land us with 5 to the n in the denominator. So therefore, we know that these will once again cancel. Now, the bottom line is the limit of this, this whole expression, negative 1 to the n times n squared, the limit of that expression as n approaches infinity, that just would not be 0 ever, right? For any reason. So for that reason, due to the nth term test for that divergence, we know that that diverges as well. So therefore, we know that the interval is going to be negative 1/5, positive 1/5 with parentheses. Okay, so similar process here. I say we just cut to the chase. We do the limit as n approaches infinity of x to the 5 times n plus 1 all over n plus 1 factorial times n factorial all over x to the 5n. Using similar methods, we could recognize that this is certainly x to the 5n plus 5. Down here, this is really n plus 1 times n factorial. Let's cross these out. X to the 5n plus 5 is really x to the 5n times x to the 5th, and we can cross that out. So therefore, these will cancel. These will cancel. And therefore, what we're looking at is the limit as n approaches infinity of what's left over on the top, x to the 5th all over n plus 1. Now we could think of that as x to the 5th times 1 over n plus 1. Now if we were to substitute infinity in for n in that case, it would be 0. So therefore we're looking at the second option, and the series converges for all values of x. So the radius of convergence would be infinity. And of course, the interval of convergence is from negative infinity to positive infinity. Okay, finding the radius of convergence with this one, similar process. So it would be x minus 7, the limit as n approaches infinity of x minus 7 raised to the n plus 1 all over n plus 1 to the 3rd plus 1 times the reciprocal of the original, which is n to the 3rd plus 1 all over x minus 7 raised to the n. And sort of whittling this down, we can recognize that this is really x minus 7 to the n times an additional x minus 7. Crossing that out. This I do not feel like working that out, but at the end of the day, we know that these will cancel. So we're really looking at the limit as n approaches infinity of x minus 7, I'll put that off to the side, times this n to the 3rd plus 1 all over n plus 1 to the 3rd plus 1. And this would turn into 1 once you substitute infinity in for n, because the degree on the top is the same as the degree on the bottom. So this is going to be one of those scenarios where it's going to be x minus 7 is less than 1, because we've just established that since this equals 1, it's going to be 1 times whatever this is, and we're not therefore resulting in 0, and we're not therefore resulting in infinity. So that leaves the only other option, which is that we're dealing with the top row. So we know that it converges to an interval, and the interval would be a matter of solving this. And we can very clearly see we're looking at x is less than 8 and greater than 6. So if we want the radius, well, we look at 6 and 8, and clearly the center right there would be 7, and therefore the radius is 1. Okay, now we need to find the interval of convergence, so let's go ahead and see what happens when we plug 8 into this. When we plug 8 into this right here, we're going to get the following series. We're going to have 1 up there over n to the 3rd plus 1. So for this one, we could use the direct comparison test, and we could find another expression, another a sub n, that is sort of comparable to the one that we have. For example, we could consider something like this. We could consider something comparable that looks like this. Now, the reality is that This denominator is smaller than this, or we could say this denominator is bigger, so therefore this whole fraction is bigger, okay? The smaller the denominator, the bigger the fraction. So we're sort of looking at this top scenario where we just chose a new expression that happens to be larger than the other one. Now, if we can show that this larger expression that we just made up is known to converge, then it must be that the original also converges. All right. So the question is does this converge? Does this series converge? Well, according to the p-series test, if p is greater than 1, then the series converges. And that's exactly what we have here. Okay, so therefore, due to sort of a combination of these two tests, we know that this converges, and therefore this has to also converge. So we know that when x equals 8, it converges, so therefore you could put a bracket there. All right, and we still have to investigate when x is 6. So the question is what's going on when we plug in 6 into that? Well, I think you can see that it would be the case that if we plugged in 6, we would have, I'll just put the -1 to the n off to the side. And that's going to be 1 over n to the third plus 1, and we're going from n equals 0 all the way up to infinity. Now, that definitely looks like an alternating series scenario. So if we're dealing with alternating series, then if we can show that the limit as n approaches infinity of this expression, not the -1 part, but the a sub n part, if we could show that the limit as n approaches infinity equals 0, well, that's one criteria. So is that true? If we just take into account this part right here, and we did the limit of this blue box as n approaches infinity, yes, that would indeed equal 0 because it would be 1 over infinity, which is 0. Okay, so we've satisfied the first criterion. So the next criteria would be comparing a sub n plus 1 and asking yourself, is that smaller than a sub n? Well, we can kind of do that down here. So a sub n plus 1, that's going to be 1 over n plus 1 cubed plus 1. And we're asking ourselves, is that less than the original a sub n, which is this? And I'm going to say that this denominator is definitely bigger than this denominator, which means that this fraction is smaller. Now, how do you know that this denominator is bigger? Well, this denominator is bigger because this part is bigger. So this will always be some larger number cubed plus 1, some larger positive number, by the way, cubed plus 1. So seeing as how, again, n starts at 1 and then goes up, right? So this fraction will, this denominator will always be bigger, which means that this fraction itself will always be smaller. So that satisfies both criteria here for the alternating series test, and therefore we know for a fact that when x is equal to 6, it also converges, which means that we're going to get a bracket next to that as well. Okay, so that's all I have time for today when it comes to these. There's lots of different problems that we could explore. However, hopefully this video gave you a sense of what's involved when it comes to figuring out the convergence, intervals, and so on for a power series and the radius of convergence for a power series. So if you noted any mistakes, please let me know in the comments. The process itself is sound. And good luck, and hopefully this helps, and I will talk to you later. Bye.